So for rotational kinetic energy, right here we have a bicycle tire. It is spinning on a frictionless spindle. Now, when we're looking at how energy is stored within the system, a natural instinct would be to say it's stored as kinetic energy. Our system is moving. However, the way that we've typically focused on kinetic energy is in terms of velocity, where the object is moving in some direction. This bicycle tire is spinning, but it's not moving anywhere. It's rotating, and we're going to need to try to figure out a way to quantify the energy associated with this rotational motion. What I ended up doing was I ended up highlighting in red one of the spokes on the wheel. That individual spoke is comprised of many individual particles. So if we were to focus on just the kinetic energy of a single particle, we can try to figure out a way to relate our linear kinetic energy to maybe the kinetic energy associated with rotation for a single particle. And then we can do that for every single particle within the system, and the sum of all of the individual kinetic energies of each individual particle would be equivalent to the total amount of kinetic energy associated with the rotational motion. So to do that, I'm going to start off with our equation for kinetic energy. 1/2 times mass times velocity squared. I'm going to be focusing on any individual particle, hence the subscript I. Our energy kinetic of an individual particle is equal to 1/2 times the mass of that individual particle times the velocity of that individual particle squared. However, that particle is not going to be moving in a consistent straight line. Rather, it is moving in a circle, in a circular path. So I can try to rewrite that linear velocity as an angular or rotational velocity. So our linear velocity is equal to our radius times our angular velocity. So if I take that, I can substitute r omega in for v. Now, that radius for where our particle is, how far away it is from that rotation point, is specific to that individual particle, hence the subscript I. Also, that mass of that individual particle is specific to that particle, hence the subscript I. However, the angular velocity of that particle is not unique to that individual particle, which is why I am not including a subscript I there. Right here, this is an equation that is accounting for the rotational velocity of that particle. But I can simplify this a little bit by distributing out that exponent. So this would be a way for us to quantify the individual kinetic energy of any individual particle within our system. However, the energy that would be associated with the rotation of the entire system would be the sum of every single kinetic energy of each individual particle. So we're going to try to come up with a succinct equation for our rotational energy by summing up each individual kinetic energy of each individual particle. So our rotational kinetic energy of our system can be quantified by summing up 1/2 times the mass of each particle times the distance of each particle squared away from the axis of rotation times the angular velocity squared. Now, only the mass and the radius are individual to each particle, so those are really the only things unique that we need to sum up. So I can factor out the 1/2 and omega squared from this. And the sum of each individual mass times each individual radius squared. That is our definition of the moment of inertia. So our equation for the rotational energy of our system is 1/2 times the moment of inertia times our angular velocity squared. Now, if I were to write some energy equations, our equations for kinetic energy are now two. We have our equation for linear kinetic energy or translational kinetic energy, which is kinetic energy is equal to 1/2 times mass times linear velocity squared. And our rotational kinetic energy is going to be equal to 1/2 times our moment of inertia times our angular velocity squared. Both of these are kinetic energy. So if we want to know the kinetic energy of the entire system, it would be the sum of the linear kinetic energy and the rotational kinetic energy. One thing I want us to note is just like when we were focusing on our kinematic equations, where we had linear or translational motion and angular or rotational motion, where they have these very similar equations just with different variables. The same can be true of our energy. We can see that's true for our kinetic energy equations, 1/2 times a term that's related to the resistance to linear changes in motion or rotational changes in motion times linear velocity squared or rotational velocity squared. They are very similar to each other. We can expand this for other common equations. For example, work. Work is the area under the curve of a force versus displacement graph. That was true for our linear motion. For angular motion, work is the area under the curve of a torque versus angular displacement graph. Power, we had previously shown, could be quantified by taking the force applied to our system times the velocity of our system. The angular or rotational analog would be power is equal to the torque applied to our system times the angular velocity. These are equations that can help us when we're focusing on the energy stored within a system that is undergoing either linear motion or rotational motion.